Along the coast of British Columbia and on most shallow rocky coastlines, from polar to temperate latitudes, kelp are extremely important species. Kelp are often referred to as foundation species because they have a significant role in structuring shoreline ecosystems and providing resources. Researchers from the University of British Columbia, Sam Starko and Patrick Martone, wanted to determine whether kelp species increase tenacity or reduce drag coefficient as they grow, and wonder whether these traits are trade-offs. Further understanding factors that influence kelp morphology and whether biological traits that help kelp survive in wave-swept environments are trade-offs could have implications for the biofuels industry and even civil engineering.
So this is probably one of the most important um, species that we have along our coast, at least ecologically. It's a summer annual, so it only grows for about 4 to 6 months of the year. But in that year, it grows incredibly fast and grows to be incredibly large. So they can grow, I believe it's up to 30 meters in some areas if the water's clear enough. This piece here is part of a big float.
Yeah.
So this will be one big ball, and that's what keeps the alga upright. So this is a really important canopy species.
Yeah.
That forms a three-dimensional habitat.
Yeah, exactly. Because they're foundation species. I didn't realize how important they are until I started reading about how they create ecosystem dynamics and stuff.
Mm-hmm. Yeah, definitely.
Many species of kelp live in wave-swept environments and are exposed to constant hydrodynamic stress. There are two traits that allow kelp to thrive in these harsh environments and avoid breakage from the substrate or rock that they are attached to. Kelp can develop a highly streamlined structure in order to reduce the amount of drag. These species often have thin, flexible blades. Kelp can also increase tenacity or attachment force by developing a larger holdfast and thicker and stronger support tissues, such as the thicker stipe.
So this is a Laria marginata, which was one of the more streamlined species. As it grows, it basically grows out as a long ribbon or a long blade like this, and that morphology with a really flexible stipe is really good at folding up and reconfiguring in flow. So this species, its main strategy then is to reduce drag or to streamline. And as a consequence, it ends up having a quite small holdfast. So this is how they attach to the rock, is just with that. If you compare that, for example, to another individual that's similar in size. Let's see if I can find it. Well, this is bigger, but you can see, it's more similar in size. But you can just see, even though this is maybe twice as big of a blade, its holdfast is probably 20 times the size or something. So quite.
In order to quantify drag, Sam Starko attached each species of kelp used in his experiment to a force transducer in a tank where the water flowed against the kelp at a speed of 1 meter per second. He wanted to see how the kelp resisted the strength of the water flow. Here's an example of the kelp undergoing high wave speeds in the experimental setup. Now this is an example of a species that has greater tenacity.
And then this is Saccharinus sessilis, which, as it turned out, was one of those tolerators. This species is unique because it doesn't have a stipe, and because of that, it has this really wide blade base at the bottom, which does prevent it from folding up. And so this only lives in wave-swept environments, and that may be because it does grow to have such a large holdfast. So, as you can see, they're just getting bigger and bigger.
Yeah.
And some of the ones I was looking at, that were that big, have a big holdfast. So it's pretty cool. It's pretty huge.
What is a fitness trade-off, and why are fitness trade-offs important in biology? A trade-off in biology exists when one trait cannot increase without a decrease in another. Fitness trade-off is an important concept in evolutionary biology and helps to explain factors that limit the adaptive potential of organisms. An important result of fitness trade-offs involves their role in maintaining genetic variation among populations within species, leading to morphological or physiological specialization. In this study, the researchers found evidence for a trade-off between tenacity and drag, having possible substantial consequences of the evolution of some species of algae, such as brown algae. There are roughly 1,800 species of brown algae, and as you can see from their pictures, some differ greatly in morphology. An example of another fitness trade-off seen in nature is the freeze tolerance strategy seen in amphibians. There have been several studies demonstrating strategies between avoidance and tolerance in amphibians, where basically amphibians that are able to tolerate freezing basically just freeze themselves because they don't have any mechanism to prevent freezing and vice versa. They do this in order to survive.